Okay. Good morning, all of you. So we will start. I hope you are able to see the screen and listen to me.
Yes, sir.
Thank you. Okay. So just before I start, there is one point that I want to mention. So I am seeing that many of you are sending query mails to both me and Pavan, but you are using our institute email IDs. The problem is that many of the times, I mean, majority of the times, what is happening that all of these are getting spammed. So I would request that if you want to send mails to me, use my Gmail ID, which is this one. And it is also a good idea to, when you are sending mails to me or Pavan, always keep the Algo TAs in CC, the Algo TA group. So, this will ensure a even faster response. Okay. So, for the last few lectures, I guess you have now developed a fair enough idea of designing greedy algorithms. So I think there has been quite a few examples that were covered that had a greedy idea in the back end. And also, I am assuming that you are now conversant with the disjoint set construction idea. So I'm assuming these things because the things that we study from now on for the next few lectures will require ideas from disjoint sets and the basic greedy algorithms. So in this week, particularly, we shall attack graph problems that can be solved using a greedy approach. Okay, so this is one thing that we will see. And the other thing is we will close with a nice comparison between the greedy and DP techniques using a fairly known example in the computer science literature called the knapsack problem. So, as I said, we will start with greedy on graphs, and the problem that we are going to tackle here are identification of minimum spanning tree in a undirected weighted graph and single source shortest path finding
Sir, can you scroll up?
in a scroll up.
Yes. Okay, sir.
finding in a directed weighted graph. In all our algorithms that we will study, weights are assumed to be positive. Spanning trees. Now, why are they important? So again, the motivation comes from real life examples. Suppose you are to construct roads connecting different cities, say in a particular state, and it should be such that a car is able to drive from any city to any other city. But then there are budgetary restrictions, and you can only afford to construct the road with minimum cost. Okay, these and similar other problems can be solved using the minimum spanning tree identification algorithm, where each node is a city and the connection between nodes can be thought of as roads, and the weight on the edges could be thought of as the weights on the edges of the undirected graph. Okay, and your task is to find out the spanning tree, specifically the minimum spanning tree. Now, what is a spanning tree? So a spanning tree is a connected subgraph of a graph G having all the nodes of G and is a tree. Okay, typically G is a weighted undirected graph. Then what is a minimum spanning tree? As the name suggests, a minimum spanning tree is a spanning tree of minimum aggregate edge weight, sometimes denoted with just a shorter form, minimum weight. Okay, so a spanning tree is a connected subgraph of a graph G having all the nodes that are present in G, but is a tree. Okay, and typically G is a weighted and undirected graph. The minimum spanning tree is a spanning tree of minimum weight, or which is basically the sum of all the edge weights in that tree. Okay, that should be minimum. That is what is the constraint. So let us see an example. Suppose we have a graph like this. So a spanning tree, say this is G. A spanning tree of G could be the following one. Okay, so this could be a spanning tree of the graph G. However, note that this is not the minimum spanning tree. This is just an example spanning tree. One of the minimum spanning trees. Okay, I already broke the suspense, but I think you are already guessing it. So this is a spanning tree of G which has minimum weight. Okay, so this is one of the spanning trees of G which has minimum weight. So as you can understand from my statements that a minimum spanning tree is not unique. Okay, and this graph itself has another minimum spanning tree. Can you guess?
Uh, Sir, V3 to V4 and V3 to V5 and remove these 5 and 6.
One could be
Sir, V1, V2, then V2 to
V1,
V3,
V2,
then V2
V2
to
to
V3,
V3,
then V3 to
V3,
V4, and
V3,
V3 to
V4,
V5.
V3, V5. Yes, sir. 2.
Sir, what did we minimize here?
huh?
So
What
which
did we?
quantity are we minimizing here?
As I said, the total edge weight. See, 3 plus 1 plus 4 plus 2, the total aggregate edge weight, as I said in the definition.
Okay, sir. So means not between two nodes, just the total.
No, the aggregate edge weight. That's where like the fun thing comes in. That's why you can use a greedy approach. Okay, so the total sum of the edge weights is what is expected to be the minimum. That is also like in general you can think of to be the cost of laying down the roads. Okay, there is a budget assigned by the government and you have to be within the budget. Okay, so based on these budgetary constraints you want to minimize the total cost that is required to lay down the roads. So, okay, so now we have motivated ourselves with the requirement of finding minimum spanning trees. Okay, the question now is how to do this. So, as engineers, we have to come up with, formalisms or a formal or an abstract representation of things. Unless we do that, it is very difficult to target for a solution. So this is something that we need to learn like very early on as engineers. So let us say that T is a spanning tree of the graph G. Okay, so then we know that the vertices in T are same as the vertices in G. And let's say that F is the number of edges in T. Okay, so therefore F is a subset of E. So from now on, we will call TVF to be a spanning tree of GVE. Okay, so TVF will be referred to as a spanning tree of GVF. Now,
So can
the
you scroll up a bit?
done.
Okay, sir. Okay, sir.
Okay, so now for computing the minimum spanning tree, what we need to do is to identify some locally optimal strategy. Now, whenever we use terms like these are very loose terms, and it is very difficult for engineers to work with these kind of loose terms. As you will see, like when you go up, you get involved in various research projects, especially your BTech projects, you will see that in many cases you come up or you land up into problems like this. These are typically called ill-defined problems. Suppose I say like identify a locally optimal strategy. It's very ill defined, right? So you don't really have an idea of how to have a locally optimal strategy. Okay. So now the process of making this ill defined problem converted into a well defined problem, okay, is what is our task. And in this process, we will learn two greedy approaches to compute the minimum spanning tree of a graph, of an undirected weighted graph. And these are called, maybe some of you have already heard the names of these algorithms, the Prim's algorithm and the Kruskal's algorithm. So these are the two different algorithms that we are going to study, which will tell us a unique way to characterize the locally optimal strategy. Okay, that is what is our task. So today's lecture, we will talk mostly about the Prim's algorithm. And tomorrow we will take up the Kruskal's algorithm. Now, what does Prim's algorithm do? It starts with an empty subset F. Recall that we have already defined F. Okay. And a subset of vertices let's call it y. Okay, and this is initialized with one arbitrary vertex. So we have an empty subset F. We have another subset of vertices Y, which we start with, which we initialize by having any one of the arbitrary vertices of the graph G. For instance, let us assume without any loss of generality that Y has V1 in it. Okay. Next, we consider something called a nearest vertex. What is a nearest vertex? So this is a vertex that is nearest to the vertices in Y and belongs to the set V minus Y. Strictly belongs to the set V minus Y. Okay. Now let us take an example, the previous one, and see what we are trying to mean here. The same running example. Now in this example, if we set Y to V1, then nearest of Y from V minus Y should be
V2.
V2. Okay, based on the edge weight. Okay, since the weight of is minimum. Okay, now we will keep adding nearest vertices to Y and the corresponding edges to F. Okay, we will terminate when the set Y contains all the vertices.
Sir, hello, sir.
Yes, go ahead.
Sir, we are selecting any one element from the set V minus Y, or we are checking all the elements?
We are checking all the elements because Y is growing and V minus Y is shrinking.
Yes, sir.
We will see with an example.
Yes, sir.
Let us look at the high level algorithm first. So as I said, we start with an empty set F and our y is v1. Now, while the instance is not solved, so what are the three different components in a greedy structure? Has this been taught? There is a selection procedure. There is a feasibility check, whether the solution is feasible or not. And then there is a solution check. Any greedy algorithm will comprise these three subparts. Okay, remember this once and for all. So there will be a selection procedure by which you select the next move. There will be a feasibility check by which you identify whether the solution that you are trying to construct is feasible at all or not, and then finally a check on the solution. Okay, so now here select a vertex in v minus y that is nearest to y. So what is this? This is selection step or feasibility check?
Selection step.
Can't hear you.
Selection.
Selection, okay. So what is the feasibility check here? What do we check here for feasibility analysis? What is the feasibility condition here?
Sir, minimum weight. So the
Huh?
minimum weight that should be connected to all the components in y, and it should be minimum. The weight should be minimum.
Yes, the weight should be minimum, but like
if the
the
vertex
first
has
step,
already been selected.
the vertices. Go ahead, go ahead.
I mean, we have already added that vertex into the subset of Y.
No, and why do you need that? What is the feasibility question here? When will you tell that the solution is feasible? Even before it is minimum. When will you tell that the solution is feasible? This is a hint, even before it is minimum.
Sir, there should be an edge.
There should be an edge.
There
Between
should be
what and what?
There should be an edge connected between that element that we are choosing and any vertex in the set Y.
Can there be like say n plus 2 edges if n is the number of nodes in this tree?
No, sir.
Huh?
No, sir.
No, sir.
No, though. You are telling no, right? Confidently.
Yes, sir, there can't be. Yes,
There
sir,
can't be, right? So this is a tree. So your feasibility condition check is whether the solution that you are approaching is a tree or not in the first place. And where is this thing checked? How will you check this?
Size
By
of
checking
F
the set F, its size, and comparing
size of F. So that means you will have to enumerate all the edges of G, and then also like in on the fly compare it with the number of edges in F. Will you go like that?
Sir, we can also check if y is equal to v.
Y is equal to V, so you will check. That's where you will terminate.
Sir, if there is no cycle.
If there is no cycle, so we will call a cycle detection algorithm here.
Sir, every time we add an edge, we increment an edge counter and check if it is less than n-1.
You add an edge that is required, right? Every time you add an edge, you have an edge counter and you count like whether the number of edges is surpassing. What is this step doing? This is only selecting. Are you looking carefully into this step?
So if we select something from outside Y, then it will always form a tree, right?
Absolutely. So that is what you are not seeing. So you are always choosing a vertex from V minus Y. So therefore, cycle formation cannot happen. You are always choosing a vertex that is outside Y. Okay. So you cannot introduce a cycle here. So therefore, this is a interesting or a tricky greedy algorithm where you have fused the selection procedure and the feasibility check into one single condition. So this is both selection procedure and feasibility check. See, you are doing select a vertex in V minus Y, which immediately ensures that you are not introducing a cycle, and then it should be nearest to Y, okay, where the minimality condition is also addressed. Add the vertex, immediately add the vertex to Y.
Sir?
Ah.
Sir, I did not understand that what we are actually trying to check in the feasibility condition here, because that we will not form a cycle anyway. Will that not be included within the correctness proof?
Where is the correctness proof coming here?
That this greedy algorithm works in that part.
No, but the greedy algorithm has to work without introducing a cycle. So here the question of the correctness proof is not whether you are generating a spanning tree. The correctness question will be whether you are generating a minimum spanning tree or not. So you have to always ensure that whatever you construct is a tree. Your correctness question will be the greedy solution should give you a minimum spanning tree. Remember, we are not constructing a spanning tree. We are constructing a minimum spanning tree. And now, finally, the solution check. So this is the top level algorithm for constructing the minimum spanning tree using the Prim's approach. We will now look into an example.
Sir, I have a doubt, sir.
Yes.
Sir, when we are comparing whether when we are selecting an edge from V minus Y, we are comparing it with the every edge that is already
You are
included
not
in Y.
You are not selecting edge from V minus Y. You are selecting nodes.
So it's vertices.
Yes.
But and we are comparing it with the vertex that is already present in Y. So
yes.
out of all this what minimum that we get, that is we include.
Exactly, that's what I told to one of your friend also. So it's a, so basically y is expanding and v minus y is shrinking, and every time all the vertices in the y are candidates of comparison. So let's look at the example and it will be clear. It will be perfectly clear.
Sir, can you scroll a bit up?
Excuse me, sir.
Yes.
Sir, the solution check condition is this na, if v is equal to y.
Yes.
Okay. Thank you, sir.
Should I scroll?
Sir, here you have given the condition in while that instance is solved. Is while instance is not solved.
While
So,
the instance is not solved, yes.
yes, sir. So what is the need of explicitly checking that v is not v is equal to y?
No, no. So this is a top level algorithm. This will be a break. So this is how you represent. So I wanted to show the notional way of writing a greedy algorithm. This is not the exact algorithm. We will write a better pseudocode, which you can immediately modify into a C program. Right? This is just for understanding that you have these three parts: the selection procedure, the feasibility condition, and the solution check.
Okay, sir.
So let us take our example. We want to determine the minimum spanning tree in so let's say y has only v1 to start with. So we start with v1. Now, what is the nearest vertex?
So v2.
Nearest vertex to y. See, all the time I am saying nearest vertex to y. So that is v2. Okay. So you include v2 into your set of vertices. Okay. So now your new y here is v1, v2. Okay. Now my question will be vertex in v minus, in capital V minus y, nearest to this whole set. This was the question you were trying to ask me multiple times. Now what will happen? What is the nearest?
V3.
V3.
V3. Okay.
And sir, I have a doubt here.
Yes.
Sir, what would be the cost of V4, like adding V4 to V1 and V2?
What would be the cost of adding
V4 to V1 and
no, you will
and
see, you will only see the nearest, like it is edges. So the cost will be infinity. For
okay.
V1 to V4, it's infinity.
Yes, sir. Yes, sir. Okay, sir.
Right?
Sir, suppose, sir, this V2 is not connected to V3 and V4. In that case, sir, how will we check?
So, come again. Well, suppose.
So suppose, sir, V2 is not connected to V3 or V4. Like V2 is
Suppose V2
alone.
is not connected to V3 as
Or
well as
V4.
V4.
Yes.
Okay, fine.
So in such a case, sir, if we first include
So
V2, then
initially V1 will be included, then V3 will be included.
sir, but still V2 is at a least distance from
Okay,
V1.
so V2 will be included. Now next, you will see in the set of V1, V2, which among these have nearest connections to rest of the V3, V4, V5.
V3, sir, because
So in
V1,
that
V3
case,
is connected.
V3 is connected to V1, so that will be included.
Okay, sir.
As long as the graph is connected, you don't have any problem. As soon as the graph becomes disconnected, you cannot use this algorithm anymore. Nearest vertex you will get. If it is connected, if the graph is connected, then one of the nearest vertices you will get. Here, once you have included V3, there is an issue. Do you see the issue?
To which we shall connect?
Which edge do we put in? In such cases, you have an arbitration choice, any one.
Sir, if there is only one minimum weighted wedge, then we shall choose that.
Then you will include that. Here there are two, so that's why you will include any one of the edges in F. Don't confuse Y and F. Again, these two are two different things, huh? So while again writing the code, you will see that these two notions are used separately. So keep this in mind. One is a set of vertex which is increasing. Another set of vertex, that is V minus Y, is decreasing, or let me say expanding and shrinking, and the edge F is expanding. Now say your new Y you have is V1, V2, V3. Who will be the next nearest?
V5.
V5, right?
Yes,
Because it is the nearest among all this. You will see which candidate is nearest to any one of the vertices in V minus Y. Okay, and in this case, V5 is nearest to V3, and that is the minimum weight edge. Okay, so therefore V5 gets included. Now the new Y becomes
sir. Sir, we will just compare the distance between these V5 to V3, V5 to V1, and V5 to V2, and
exactly.
whichever is minimum, we'll take it.
We will maintain some data structures which will make it easy.
Okay, sir.
When we will write the algorithm, we will maintain some easy data structures that will make things easy to find. What you exactly need to compare, those things will be very easy at your hand's distance. Okay, that's what we will do when we write the pseudocode.
And sir, whenever we find the minimum, we directly make it an edge, right? For finding,
Yes,
for
of
making
course,
it.
of course. So at this point, okay, so let me mark the edges with a different color. So at this point, this edge has been included. At this point, this edge and this edge has been included. At this point, this edge, and this edge has been included in F. So those red colored ones show the content of F. And then finally, you will include V4.
And sir, last element we can add without any checking, no sir?
No, the last element, you have to add the minimum weightage, na?
Yes sir, yes sir, yes sir. Yes, sir.
You cannot do that. And it might be connected to multiple nodes in the graph. And these edges represent your edges in the minimum spanning tree. And as we had already said that there could be two minimum spanning trees in this graph. We have computed one of them based on the arbitration that we did here. Now the question is how to code or at least develop a pseudocode for constructing the greedy approach that we have seen just now. Okay. So how do we do that? So here what we will do is again like the dynamic programming algorithm that I showed you, we will conceive of a adjacency matrix. Okay. Where Wij is defined as okay. So if they are same, then the cell entry is 0. If they do not have any edge between them, then the cell entry is infinity, and showing that it's a like infinite distance or infinite cost, whatever it is. And if there is an edge, you put the corresponding weight. Now, as I told you that we will maintain two data structures, which will make our make writing our pseudocode very easy. The first data structure is what we call an array which we will name nearest I. So nearest I is the index of the vertex in Y nearest to the node Vi. Of course, Vi is in V minus Y. Okay, so that is how nearest I is defined. And a corresponding one-on-one array distance I. Can you guess what this will
Sir,
be? Yes.
sir, I have a problem in nearest I, sir.
Huh?
Sir, index of the vertex in Y nearest to the node Vi means I didn't get this, sir.
We will discuss.
Okay, sir.
Index of the vertex in Y nearest to node Vi. Okay. So in Y, you have started with V1, right? Now then there are, think of your example. There are V2 to V5 nodes in V minus Y. Okay. Agreed? Now,
Yes, sir.
now you are asking, we are telling that you build nearest to. Okay. In this case, nearest, since Y is consisting of only one vertex V1, nearest of 2 is 1. Index of the vertex in Y nearest to node V2. Similarly, nearest of 3 is also 1. To initialize, all the nearests are equal to 1. And this we will keep changing as the algorithm iterates. Is this getting better? Is the understanding getting better?
Yes, sir. Yes, sir.
Sir, but 5 and 1 are not connected. So shall we initialize that also to 1?
What?
For nearest of
Nearest of?
5.
No, I can't understand. Nearest of 1.
Sir, vertices which are not connected to 1 should also be initialized as nearest as 1.
Yes, yes. So that's what I'm telling. All of them. All the nearests. So I is like running from everything, running in everything in V minus 1. Okay. Now what should be distance I?
So the corresponding distance between the two
Yes.
nodes.
So weight of edge between Vi and the dash
Nearest of I.
and the vertex
Nearest.
indexed by nearest of I. So these are the two data structures that we will maintain. So to start with, as we said, Y is set to V1 and nearest of I for all i's, okay, not equal to 1 are set to 1. And what will be the distance?
Wi1
Is the weight of the edge connecting V1 and Vi, right? To start with, this is the initialization step. Now, in every step, you will expand this Y based on the smallest distance, okay? Based on the value of distance I, okay? So every step Y is expanded with that vertex, okay, which has a distance I that is smallest. Okay. Let us call the index of this vertex to be V near. Okay. So the vertex indexed at V near, or indexed by V near rather, indexed by V near is added to Y, and what else we have to prohibit?
So we should add edge to the F.
Yeah, that edge will be added, but we have to still prohibit the cycle formation. How will we do that?
You have to check whether this vertex is already added or not.
That will not be added because you are including it from V minus Y. But after that, you have to stop. Every time you add a vertex that is indexed at V near or indexed by V near, you have to remember that this vertex has been added and therefore should not be considered anymore. And what is this consideration based on?
We should remove it from V minus Y.
How do you manipulate the two data structures, nearest and distance, to bring that into effect, to bring that removal into effect?
You can put something like
So
minus
distance
1.
I will be 0.
Distance I, distance V near,
0.
0 cannot be, right?
Maximum.
Yes, sir.
Set this to some negative distance. And as we have said, that this graph cannot have negative edges. So this means that in the subsequent iterations, do not use it. Okay.
Sir, can you explain this?
So basically, you have understood what is V near?
Yes, sir.
Okay. So distance of V near, what does this indicate?
The distance between the Vi and the V near. I mean, the V near is in Y.
Okay. And if that, so you have already compared that distance because that was the minimum distance, smallest distance.
Yes, sir.
Now, if you do not change the smallest distance, every time this will keep on coming as the smallest distance, and you will keep on including this edge. So that's why we change this particular distance I. This distance I now is distance V near, right? That we change to some number which is very different from the edge weights. It's a non-positive number. And therefore, next time when I takes up the value of V near in any iteration, we know that we should not compare this distance. That has already, V near has already been included in Y.
Sir, but why will we come to this Vi again? We will already include that. So we will not come to
How
this
do we
step.
know which Vi we have included?
Sir, we can
We are
maintain
running on a loop. We are running a loop. We are running a loop on all vertices. Every time we are running a loop on all vertices.
Yes, so, sir, if we are running a loop on all vertices, then we have to do this. But
That's what we are doing. We don't want to maintain any other additional data structure.
Okay, sir.
Okay. So now with this paraphernalia in hand, we will write the pseudocode. This is the adjacency matrix. Set of edges is a data structure.
Sir, for storing the set of edges, we can also use another adjacency matrix.
You can, but now since you have learned disjoint sets, I am assuming that you are aware of this kind of data structures.
Okay, sir.
These are the two data structures that we are maintaining. We set F to null. Now, to begin with, what are we doing here?
So initializing the values.
Initializing the values, all assuming that Y has V1
One.
and all other nodes, the nearest is set to 1 and distance is set to the weight of the edge between the vertex 1 and the corresponding vertex I. What here? You are checking the minimum distance, and at the same time you are ensuring that it should not be less than 0, and you are setting the distance I to this minimum value. Sorry, you are setting mean to this value, okay, to the minimum distance. What else do you need to do here?
Index
Store
V
the
near.
V near.
whose index we have to store and where will you store it?
I
It will take
and V near.
another integer.
V near will be set to
I.
I. This is the nearest vertex because it has the smallest distance. Okay. So in the for loop, this will be revisited, mean will be updated, V near will be updated. Okay. And finally, you will get the minimum distance. Okay. And also the nearest vertex. Now we will have to construct E. E is the edge connecting vertices indexed by dash and dash.
Sir, VI and the corresponding
Who is VI?
V
There
near
is no
and
VI.
nearest to V near.
V near.
V near, okay? V near
And
and
nearest to V near.
And the
Nearest
nearest to the V near.
nearest to V near. Okay, so these are the two vertices which construct the edge. The nearest to V near was already there in Y, and now V near is getting included into Y, and the edge E is getting added to F. Immediately,
-1.
huh? Sorry,
Minus
minus one. Yeah, minus one. So that you prohibit cycles. Now, are we done? What will the adding process of V near result? What will adding V near conceptually result into?
Nearest array will change.
What are the data structures that have to be updated due to inclusion of V near in Y?
Nearest.
Only nearest?
Nearest and distance.
Nearest and distance. The two data structures need to be updated. What is the condition? To set distance?
If
The
W,
initial matrix I and V near less than distance I.
What will we do?
We'll update distance I and nearest.
Distance I will become what?
WI V near.
WI V near.
And
Nearest
nearest
I
will
equals
become
V near.
V near.
so. This is the part where what you are doing is you are virtually adding the vertex to Y, and you are doing another thing. Okay? So each vertex that is not in Y, you are updating its latest distance. Based on inclusion of veneer, updating. Okay, so updating its latest distance based on inclusion of veneer.
Sir,
is this clear?
Sir, can you explain this part if Wi veneer is less than distance?
So what is veneer? Veneer is the index of the vertex that you are adding to Y, right?
Yes, sir.
Now, so now a new vertex has been added to Y, right? Think
Sir,
like
veneer.
This.
Veneer is added to Y.
New vertex veneer has been added to Y. Now, since as soon as this new vertex is added to Y, you need to check for the distance of this node with all the vertices that are in V minus Y.
Yes, sir. Correct.
And you are checking that. And if that distance is larger than the distance between this particular node and veneer, then you have to update that distance. Because veneer's distance to that vertex I could be the smallest, potentially it might not be the smallest. In that case, this condition will be false. However, if it is smallest, then you need to update the distance and as well as the nearest vertex. So that means the nearest vertex to Vi from the set Y is now veneer, as well as the distance now of that vertex from Y is the distance between veneer and that vertex. Am I clear?
Yes, sir. Understand.
Okay. So we will stop here, but tell me the complexity quickly.
Sir, order n squared.
Order n squared. Order n squared. Because there are two n-1 loops. Okay? In the worst case, the order is n squared. Now I will give you a food for thought. We will do this tomorrow explicitly. How to show that this greedy algorithm always generates minimum spanning tree. Think about this. While you study the algorithm, try to think about how to show that this algorithm always generates a minimum spanning tree. So we'll stop here and we will take up with the with this proof.
Yes, sir. Here.
Down or up? Further up?
Sir, little down. Sir, we can make this for loop before that one also.
Huh?
Means, sir, we are in the while loop, we are having two for loops. So we can interchange their positions also.
Can you think about it? You can't, because the initialization also goes through.
Okay, sir, I will
Sir, what do you have written there? Updating its dates plus distance. What is
Updating
that?
its
What is that?
latest.
Okay.
Also, sir, we're checking whether distance is less than 0 or not. Should we include that condition also?
Because if we are not doing that, we might include cycles.
Yes, sir. So where shall we include that?
Kiana, we did it here. Every time the while loop is coming here.
Yes, sir. Okay.
Okay, guys, we'll stop here and we'll start from here tomorrow.
Thank you, sir.
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 Yeah, I always keep on forgetting to stop the recording.